My name is Jeff Larkin. I work in the developer technology organization at NVIDIA. I work specifically on doing a lot of porting and analysis of applications on supercomputers, on HPC-type applications. I also happen to work on both the OpenMP and OpenACC specs. I'm on the technical committee for both of those. This work was done in collaboration with James Beyer. James Beyer is also a member of NVIDIA. He's a senior runtime engineer at NVIDIA. He is the co-chair of the Accelerator Working Group for OpenMP and has been involved with OpenMP for quite some time as well. So this is an outline of what we have to cover, and we have about 80 minutes to do it. And this is not hands-on, so those of you who are in my morning session don't have to worry about Quick Labs dying again. This is not hands-on. But we are going to go through and kind of give you a background of how we got where we are in terms of OpenMP. And then we have a code that we've taken through and incrementally added OpenMP directives so you can see how to do that. And talk about some additional experiments we did and then draw conclusions. So why are we doing this? What is the purpose of this talk? We're just now beginning to see compilers come out that support OpenMP directives, the 4.0 and 4.5 directives targeted at NVIDIA GPUs. One of the most prevalent ones, the one that's really moving very quickly, is the CLANG compiler that we have been using, the CLANG compiler for these experiments. And that work is being done in a collaboration with a lot of different companies, but IBM is taking a big role in the development of that. And also, the GCC compiler has some support for OpenMP 4.0 offloading, and there is a branch working on supporting NVIDIA GPUs. So those compilers are beginning to come out. None of them are really fully mature yet, but they are beginning to come out. And we have seen people talking about using them. We've seen papers written and blog posts written explaining using them. And one of the things that we really want to show you is, okay, what's the right way to use them? Because some of them will show you one way, some of them will show you a different way. Some of them will show you completely the wrong way. And we want to make sure that you, if you choose to experiment with these early pre-release compilers, that you have some idea of what the appropriate way to use them for GPUs will be. So try to give you some idea of what to expect. Now let's give you a little bit of a history of OpenMP, because it really helps you to see how we got to where we are and what. I'm going to try to step down here so that I'm out among you. How we got where we are and why the directives look like what they do. So OpenMP was founded in 1996 by a group of companies who were working on shared memory parallel processors. In this case, we're not talking about multi-core CPUs. We're talking about entire supercomputers that were shared memory parallel. And multiple vendors were writing compilers with their own sets of directives for their own hardware. And their customers said, we're not going to deal with that. And so they got together and they formed this group called OpenMP. And in 1997, they released the first version of the spec, which was a unified language that all of them could support for doing shared memory, thread-based parallelism on their machines. And something to note is that actually, at that time, OpenMP was actually two separate specs. There was a Fortran spec and a C and C++ spec. And it wasn't until much later that they actually unified together. So you'll see in 2000 and 2002, they both iterated to 2.0, but didn't even iterate at the same time. Now, 1.0 had everything that most people think of when they hear OpenMP. It had parallel regions, and it had ways to break your work across threads. It had all of these things that you have experienced and learned about when you're learning about OpenMP. How to take a loop and spread it across threads. That has existed since 1.0, and for 2.0 and 2.5, really it was just refinements on those. Matter of fact, the biggest reason 2.5 came out was it unified the languages together into one specification, which really has helped with adding more features and being able to support more things by having them in the same spec. It wasn't until 3.0 we began to see significantly new features come out for OpenMP. 3.0 introduced tasking. Tasking is a way of, instead of just saying, I have this loop, and I want to run this loop across threads. And also, you could say, well, I have this section of my code that does something, and this other section of my code that does something else, and those two parts don't depend on each other. You can run them concurrently on threads as well. So that's where tasking came in and was refined further in 3.1. So the major features of the 3 series was to have tasking. When OpenMP 4.0 came out, it took an even bigger departure from the traditional OpenMP, what we call work sharing, and I'll define that in a little bit, and added support for offloading to other devices. Now, I think it's important to note that there are other things in 4.0. There's other really key things in 4.0. But when people say OpenMP 4, most of the time they're referring to taking it and offloading it to another device. It's just kind of become synonymous with that. 4.5 came out last year, and actually most of the compilers are just now starting to experiment with 4.5. 4.5 was a release where we really learned from what the implementers, as they were building 4.0 compilers, they said, you know, we kind of did this wrong, and we kind of fixed those. Or, you know, here's something that, that users have told us they really need. Let's add that. So it really was a refinement release. And so 4.5 came out last year, and the compilers are just working on implementing it. The version of CLANG that we did all of our testing on still has 4.0 behavior. So, but they are in the process of working on 4.5. All right. Now, what's the kind of history of OpenMP and CLANG? Until very recently, the CLANG compilers had no support at all, even on the CPUs for OpenMP. It's taken really a multi-vendor effort where you have people like Intel, IBM, TI, a lot of different vendors all working together to bring OpenMP into CLANG, because CLANG and LLVM has become a very commonly used, very important compiler. It really started off as a research project and now has become a very important compiler. And the current status is kind of interesting to work with. It took us, between the two of us, many man-days worth of effort just to get a compiler built and working. And once we got it built and working, it took some more experimentation to really get things going. But there is some information that you can find here on this site, and these slides will be available later on for download, that you can go and read up about the current status. So if you are interested in doing these experiments yourself, we will make the source code available for you to look at. But I will advise you that building CLANG and getting the offloading working is a chore. At this point, it takes a lot of work. And but like I said, between the two of us, several days worth of effort to really get this going. But nonetheless, if you do go through those efforts, you will get a compiler that is capable of working. So first off, you will need some tools, and I don't need to go through all of this because these are more for reference later on. But you'll need to have a variety of tools installed, and go read these documentations, and you can get it working. Notice we are not actually building from the trunk here; that we are building a version that is available on GitHub that came out of the IBM team, and it's in the process of being folded into trunk. Again, this is for some reference here in case you want to go back and do it. You don't necessarily see that. But I do want to show you that it's not the simplest thing to use, even once you have it built. I'm sure it will get better, but there are a long variety of environment variables you'll need to set in order to get it working. And so when you go home and decide to try this, keep in mind that you'll need to set a lot of these variables. But eventually, things will boil down, and you'll get something working. OK. So there's the background. Let's get into the actual coding here. So we're going to do this case study. This is a code that we've used in a lot of parallel programming tutorials. You've probably seen us use this code before. It's the Jacobi iteration. So this is a way of a technique of iteratively refining your answer based off of the previous iteration, and eventually getting down to your final answer. Now, we're going to be solving the Laplace equation here. So what we're going to do is, if you see this red dot here, imagine I need to figure out the temperature of that dot. Well, the way I'm going to do that is I'm going to look at its neighboring cells. And the neighboring cells, they all have their own temperature. And I'm going to look at their temperature. I'm going to average it together, and that's going to become my new temperature. And then I go on to the next iteration and do the same thing, and the next iteration do the same thing, until eventually I arrive upon either the right answer or a good enough answer. So that's the code that we'll be working on here. And this is what the actual code looks like. And you'll be seeing whoa, somehow we got to the very end. All right, so here is what the actual code looks like. You can see we have a while loop on the outside. That's our convergence loop. This will continue to iterate until one of two things happen. Either we reach convergence, which is defined by, if we look at all of the different points, they have all stopped changing by some tolerance that we've set, or we reach a maximum number of iterations. So for all of the data we'll show, we go 1,000 iterations. Just to be fair. The top loop here calculates the next value. So I look at go to every point, look at its neighbors, I calculate what its next value will be. I figure out my rate of change to get my error tolerance. And then down below, I have a second loop nest that exchanges the values of those arrays. And inevitably, when I show this code, people will point out that in C, you can do pointer exchange or something like that to make this run a little bit faster. But that's not really the point of this. The point is to make this pretty simple to understand. We have our loop nest that calculates the next value and our loop nest that swaps. And that's all we need to work on. All right, so the first step here, since we're using OpenMP, is we're going to start off by parallelizing on the CPU. The CPU compilers are very well tested. They're very well understood. They've been around, in some cases, for decades. And so we want to start off by parallelizing on the CPU. And a lot of people have done this before. They know I go into my C code and I type OMP parallel 4, or I go into my Fortran code and I type OMP parallel do. But I don't think as many people truly understand what those directives do. So we wanted to break down for you exactly what these directives are doing. So the parallel directive. The parallel directive spawns a team of threads. Remember that phrase, a team of threads. It'll be important later. So if we look on the right, I encounter parallel. I have my thread comes in, it hits a parallel. It creates this group of threads. In this case, I'm showing 4. That's called the thread team. And what happens to my execution? It continues on all of the threads. So all of the threads are redundantly executing. Now, I've highlighted this one thread here that's red. That's the master thread. Every thread team has a master thread. And typically, what comes in, and if not truly, but in a logical sense at least, the same thread that comes into this region will become the master thread, and then will be the one that continues on. And that's how the execution will work. So this is known as a fork join model. We encounter the parallel region, we fork 4 threads in this case. At the end of the parallel region, we join them back together. This is what the parallel does. Now, there's also a matching directive called the loop directive. In C, this is the for keyword, and in Fortran, this is the do keyword. What the loop directive does is it takes the next loop, so I always put this immediately above a loop, and it divides that work across these threads that I created. So this is a technique called work sharing. I have work. I want to share it across my threads. So you can see on my green box, this changed from being redundant to being spread out across these threads. Now, how that's divided, how I take those loop iterations and give them to the threads are determined by something called a schedule. Again, remember that term because it's going to be significant later. So we use a schedule to determine how the iterations are spread out. So this is what an OMP parallel 4 does. Creates a team of threads, and it then the 4 spreads the iterations across them. So there's a few different ways that I could put those in the code. I think most OpenMP programmers would write it like this. I come in, on each of my loops, I have an OMP parallel 4, and that will take the J loop, and only the J loop, and create a team of threads and spread the work across those threads. What happens to the I loop? Well, that's up to the compiler, but most of the time the I loop is going to be run sequentially within each thread. So this is how I think most programmers would write this. Some of them might do it a little bit differently. Some of them might choose to use one parallel region. especially if you've been doing OpenMP for a while. I think some of the people who have more experience with OpenMP have a tendency of writing it this style because creating the threads used to be really expensive. Now, all of the compilers have figured out how to do this now, but it used to be really expensive. So older codes frequently have one parallel region, and then they'll have two fors. Now, in the case of this code, in order for this to work, I need to synchronize in the middle, so I put a barrier there. The reason for that barrier is this second loop nest requires the first loop nest to have completed. Otherwise, I'm going to potentially have the wrong answer if one thread executes very quickly and it begins writing into the array before the other threads have stopped reading. So this barrier is significant. And in fact, the first time I wrote these slides, I left off the barrier, and it took me a while to notice it because I was getting the right answers, but it was actually the wrong code. So that barrier is important because it limits the scalability of parallel regions. Parallel regions always have the threat that there could be a barrier in them. And that is one of the reasons that we really need to work on expanding the parallelism when we're running on the GPU, is to make sure that we have as few of these synchronizations as possible. Now, some compiler vendors would actually want you to write a third version of this, and I put it up there very briefly. They might want you to do this. OMP parallel 4 on both the loops, and an OMP SIMD on the inside. So SIMD is one of those features that's also included in OpenMP 4.0 that doesn't get talked about quite as much. It is a feature that it tells the compiler this is a loop that you can and should generate SIMD, or single instruction multiple data, instructions for. Now, some compilers will choose to ignore it. They're actually free to ignore it. It's the only directive right now in OpenMP that the compiler is allowed to ignore. But some compilers will say, I already knew that. I'm going to throw this away. And some compilers would say, well, thank you for that information. Now I'm going to do something faster. So some compilers might want you to do it this way. But for the point of comparison, we ran all three of these. Actually, the CLANG does not currently support this version. But we ran all of them. Their comparable performance looks something like this. So this is on a fairly modern CPU. You can see we get reasonable speed up to about 8 threads, and then it starts to tip over. That's because this calculation is really limited by memory bandwidth. The more threads you throw out, you're not getting more bandwidth. So eventually, it does kind of tip over. And so this green bar is going to be our point of comparison for all of the rest. We were able to get about 3.5x speed up across 8 threads on this Xeon CPU. OK. Now what? Now we want to target it to the GPU. So for the GPU, we're going to use something known as the target directive. This is something that was added in OpenMP 4.0. The target directive takes your thread of execution, that arrow that came into the thread team before, and says, take that thread, move it somewhere else. It could be another CPU. It could be a GPU. It could be a DSP. It could be an FPGA. It doesn't matter. We're taking the thread of execution, and we're moving it elsewhere. And in order to move it somewhere else, we also need to move the data. Or we may need to move the data. It's possible that they share a memory space. It doesn't matter. But we're going to relocate the memory and the data it needs, or excuse me, the execution and the data it needs somewhere else. Some things to note about this, and we're going to use it to move from the CPU to the GPU. Any data that's moved over to the device, so any data we move to the GPU owns. And if you begin to access it on the CPU while the GPU is accessing it, the GPU wins. It's owned by the target device. Next, and so anything else, it's forbidden. If the data that you use in that region may be put on the GPU either implicitly by the compiler or explicitly by you. And this is a process known as mapping. I have a host array, and I'm going to map it to a device array. And it's going to create this association. In fact, they could be the same array on some devices, but it doesn't matter. Logically, there is this mapping that occurs from the host to the device. So that's the process is known as mapping. Now, some people would point to this last bullet as one of the strengths of OpenMP, and some people would actually point to it as one of the weaknesses. This is a point of contention that people will disagree on. All of OpenMP is allowed within the target device, in the target region. So anything you can do anywhere else in OpenMP, you could say target to move your thread of execution, and then do the rest of OpenMP over there. So while you can do all of OpenMP on the target device, not all of it will perform well on the GPU. So you really need to think about, once you get onto a GPU device, writing your code in a way that is appropriate for the GPU. And so actually, in this first version, we did what I think a lot of programmers think they want to do. And they said, I've got an OpenMP code. I'm just going to put target, and I'm done. I take it, I move it over to the GPU, and it's just going to run well. And that's all this code does. In this version, I'm letting the compiler implicitly determine what data needs to be on the device. So A and A new are going to be relocated from the host to the device. So are all the scalars. So all of the loop parameters, N and M, are also going to be moved over. And error is going to be copied back because it's needed by the while loop. I can actually make that explicit. There's a clause known as map where I can explicitly control this. So here I'm saying allocate space for A new, and I'm giving it the bounds of A new, and copy, so map A to the device, so from the CPU to the GPU, and then at the end map it back, copy the data back. And so that's what we're showing here. And so for our data, we'll show this version because it performs slightly better. You don't have to do quite as many copies here. So we'll show the performance from this. But it turns out the performance is pretty bad. So if this is our original code at our 1.0 baseline, we went from a little over 100 seconds to just shy of 900 seconds. Performance just tanked. And I wanted to show this because I think there are people, actually I know for a fact, there are programmers who think that this is how they're going to program for the GPUs. They're going to take their existing OpenMP, put a target directive in front of it, and they're done. So why did this performance get so bad? And in order to discuss that, I need to give you a little bit of background on GPUs. Now, I recognize a lot of your faces. I know a lot of you have been to this conference before and already know a lot about GPUs. But a GPU is made out of a bunch of parts. So on the left here is a Tesla K40 GPU. And I've zoomed into one of these 5 quadrants. So I guess it's not a quadrant if it's 5, but there's 5 portions here. And you can see inside of there that inside of each of these, if you look very, very closely, you'll see the repeated pattern 3 times. I've highlighted one of those. And this thing right here that I've blown up is what we call a streaming multiprocessor, or an SM. An SM is the Lego block of GPUs. This is the most basic part of a GPU. And if you buy a mobile GPU, you'll probably have like 1 of them. If you buy a K40, you're going to have like 15 of them. Depending on the size of your GPU, you'll have a different number. But it's built up of these independent parts. All of our GPUs from across the line are built up of these parts, these SMs. So what's significant about that? Well, all of these parts, because we can scale the size of our GPU according to how many of these we put on the silicon, they are completely independent parts. They don't synchronize with each other. They operate completely independently of each other. Some of them on silicon might be turned off or turned on or whatever. So these are the building blocks that are independent of each other. So when we program for them, from a software level, we take our work and we break it up into something we call thread blocks. A thread block is a group of threads, a group of executing units that work together. Now, threads within the same thread block are always going to operate on the same SM. So threads within a thread block can talk to each other. They can share memory. They can synchronize with each other. They can have barriers, do all of these things. They can even communicate through registers. They are very closely knit. But threads in different thread blocks cannot synchronize or communicate with each other. They might be running on the same SM. They might not. They might not even be running at the same time. So you could have more thread blocks than you have SMs, and you can't know for sure whether they're all going to be active and communicating. So that's why we have these scalable parts. So we have the scalable part on the hardware is the SM, and on the software it's the thread block. It's this thing that we break our work into that works fully independently. So why is this significant? Well, in OpenMP, we have, well, I'll leave it on the slide. On OpenMP, we have this thing we called a team of threads. And if you recall earlier, inside of that team, I had a barrier. A team has the capability of synchronizing. There might be a barrier because some part of the code isn't parallel, or there might be a data dependency. There might be a critical region because I'm calling into a non-thread safe library. There might be a lock that prevents two threads from accessing the same unit at the same time. All of those things are possible within OpenMP, within a parallel region, which means if the compiler wants to be able to generate a parallel region, a thread team, to be able to run on a GPU, the best it can do is run in one thread block, because a thread block is the lowest level where all of those things are possible. Now, if a compiler has full vision of the entire program and knows absolutely everything, it may be able to determine that, you know what, it's safe for me to throw all of that out the window. But if the compiler wants to strictly adhere and truly know for sure that it's doing something that's safe, the best they can do is run an OpenMP parallel within a thread block, which means I'm throwing away a whole bunch of my hardware. So the first thing we need to do to make things run better on the GPU is spread things out, or as I put it here, we need to team up. So instead of running on one team, what if we could generate multiple thread teams and spread them out? So this is another feature that got added to OpenMP 4.0. Prior to 4.0, we had this notion of thread teams, but there was always one. There was one thread team. In 4.0, a new directive was added called teams. And what it does is it generates one or more thread teams. And the compiler might choose to generate a bunch of thread teams. The user might generate to do a bunch of thread teams. It might choose to do one. But it's a scalable directive that lets you spawn more than one of these thread teams. Now, it looks a lot alike, right? All of these thread teams are going to have the same size. And all of these thread teams are going to have a master. And once we encounter the teams directive, we create these thread teams. Execution is going to continue redundantly on the masters of all of these thread teams. So that's what this does. Something to note is these thread teams can't communicate with each other. There's no barriers. You can do a reduction across them, but you cannot do a barrier across them. You can't have critical regions across them. They can't in any way communicate with each other. So this is the scalable building block. Now, we're executing redundantly. Let's fix that. So just like we had the loop directive before, we have the distribute directive. The distribute directive takes the next loop and breaks it up across the thread teams. Now, at this point, only the masters are executing. So now all of the masters have gotten some chunk of the loop that's being distributed. And they can then, if they want, work shared across threads in the team or not. Now, a few things to keep in mind as you're implementing this code. First off, this distribution is done statically. So when you encounter the distribute, it's going to break that up right then and distribute it across the team. So there's no room to go back and try to dynamically load balance anything. Also, there's no guarantee of order of execution between the thread teams. There's no guarantee that the first thread team generated will complete before the last one, or in any order like that. They can run in any possible order. They might sequentialize. It could be that there's only enough hardware to run one thread team at a time, and they're just going to be run in order or a random order. It doesn't matter. There's no guaranteed order of operations between thread teams, and no guarantee that they'll all run simultaneously. And I already covered that last part. So here's what the code. Before I can move on to the code, I need to introduce one more concept, and that is the OpenMP target data directive. So it turns out before we can add teams and distribute to our code, we need to change the way our data is handled. So the target directive took the thread of execution and its data to the device. The target data simply moves the data. And then it relies on sometime later on, you're going to move your thread of execution. And the reason you would do this is if you have multiple target regions, which we're just about to have. So I have a target data, and then inside that 2 target regions, that I want to share my arrays. And so that's what this is done for. Interesting bit of trivia. A target region is a target data region. So that means any clauses that you can use on a target data region, you can also use on a target. So that's why we had those map clauses before. Yes, there's a question. Can the target be a CPU? Absolutely. The target can be anything. Really, the target can offload back to itself. You still are better off exposing the data movement, because unless you know you're always running on targets that share arrays with their host, you still want to do the mapping. But yes, the target could be a CPU. It could be anything. Question?
Target data directive always valid for a structured block, or is it like OpenACC can be
So the question is the target data always structured? So the target data itself is always structured. There are unstructured directives as well. They were added in 4.5. It's a target enter data and a target exit data. We don't cover them here because they're not supported in CLANG yet, but they are available as well. OK, so let's look at the code now. So here's the new code. I added the target data region on the outside, so that's around my while loop. And the reason I did that was I now need 2 target regions inside of this. I can no longer do this in one target region. Now, why is that? Well, I mentioned earlier that this loop nest down below must wait until the loop nest up above has completed. I also mentioned I can't synchronize between teams. So the only way that I can ensure that the bottom loop nest waits until after the top one has completed is to break them into 2 separate teams regions. So what I've done here is I have a target teams that generates 1 thread team. That one's going to fully execute before the next one starts. Now I want to go left to right on this and make sure we talk about every one of these directives, because as you can see, OpenMP can get very, very verbose. And so it's important to understand what each part is. OMP target. Target relocates my execution. Teams. It's going to generate 1 or more thread teams. In the case of this code, what the CLANG compiler is going to do is it's actually going to generate 15 thread teams. Why? Because there's 15 SMs on the GPU, and that's how they chose to implement it. Distribute. Take the J loop, spread it out across those thread teams I created. Parallel. Activate all of the threads inside of my teams. 4. Work share within the teams. So I'm slowly building out all of my parallelism. And so that's what this is here. As you can see, it took a lot of typing to get to this point. And it's only going to get worse. So what does the performance do? It pretty much brings us back in line. So again, this is a K40 against an Intel multi-core Xeon. And you can see we basically got back to our single-threaded performance. So it's a start. We're not 9x worse anymore. We're now at least comparable. So what next? Well, the next thing we need to do is we need to look at our parallelism. So far, everything we've done has focused on our J loops. Our I loops are really just still sequential loops. So we break up, we distribute our J loop, we parallelize across our J loop, and those I loops, well, that's parallelism we're not exploiting. And on a GPU, you want as much parallelism as possible. So we need to tell the compiler to do something with the I loop. And we're going to show you 2 different ways to do that. So one option. I can break up my teams distribute and my parallel 4. So teams generate thread teams on the J loop. Parallel 4 parallelize or work share within the thread teams on the I loop. So that's one possibility. The second is something called collapsing. So collapsing is when you have 2 or more loops that are nested together, and they have to be tightly nested, that you then squash them together, linearize it, and make one really long-running loop. So if I have a loop with n iterations and a loop with m iterations, I can have a single loop that's n times m iterations. And so OpenMP provides a convenient way to do that. I know the C programmers probably do this all the time. But OpenMP provides a convenient way to do this that says collapse, and then you provide it with a parameter. And the parameter is how many tightly nested loops to collapse. So in our case, we have 2 loops. We'll collapse 2. And so this gives us a lot more parallelism to work with. So we can distribute or parallelize across any of those loop iterations. And so this is the first approach. The first approach is teams distribute on the outside. So take my J loop, spawn thread teams, spread them out across the thread teams. On the inner loop, parallel for. Take the I loop and run it across the threads of those teams. And I did that for both of them. The next approach is the collapse approach. The collapse approach says take those two loops, flatten them first, and then apply a teams distribute parallel for across them. So what are the trade-offs with these? The first one, once again, I'm only distributing the J loop, and I'm only work sharing the I loop. And so if one of the, depending on the sizes of those, there still may be some parallelism left on the table, right? Because once I get inside of my the threads on my I loop, some of the loop iterations may be run by the same thread. So I might not be getting quite as much parallelism in this case as I am with the other case. With this case, the compiler is free to use all of the iterations however it wants, or you, the programmer, because OpenMP is completely explicit, as you've seen by the length of this. You're completely explicit about what you're doing. So you also have the option to say, to go back later on and say, OK, well, I want to run this many threads and this many teams and figure that out. So our expectation is that this was actually going to outperform the previous one, because it gives the compiler a lot more to do. And we were wrong. The compiler actually liked the split one better. We slowed down a little bit with the collapse, which we never really dug into exactly why. It kind of surprised us a little bit. But you can see we're now up to 2.5x performance improvement on the split version, where we have the target teams on one loop and the parallel for on the other. But we're still actually losing to the CPU. And now is where it's going to start getting into, I suppose, really GPU-oriented optimizations. So up until this point, arguably, you could probably run this on a CPU. The teams by itself is not allowed on the CPU, but the compiler is always free to generate one thread team, and then you're basically where you were. So up until this point, things were probably OK on the CPU, although not necessarily exactly how you would do it. But now we need to look at how the loop is scheduled. Because it turns out that how the OpenMP loops are traditionally scheduled, because we're coming from traditional CPUs, works really badly on GPUs. So I mentioned the term schedule before. A schedule is how this loop, how the iterations of this loop are broken up and spread out to threads. So most of the time, and when I say most of the time, I mean we have talked to all of the implementers who participate in OpenMP, and every single one of them do and always have taken a static schedule where they say, I have n iterations, I have 4 threads. Let's say I have 100 iterations and 4 threads. The first 25 will go to thread 0, the next 25 to thread 1, and so on. Every compiler currently available that we know about does it that way. And they don't have to, but they do, and always have. Now, some of them have hinted that they might look at other schedules in the future. What other schedules? Well, you can change the chunk size. So maybe you have smaller chunks and you spread them out in different ways. So you might do 10 iterations, 10 iterations, 10 iterations, 10 iterations, and rotate, something like that. You might dynamically schedule it so that if there's a load imbalance, that will try to balance out. That has its own overheads. So there's also the guided schedule that tries to alleviate that. All of those are available. None of the compilers do it by default. Now, if you have a very load imbalanced code, you've probably at least played with the schedule some. So this default schedule of taking contiguous chunks of threads and handing them out to CPUs works great on CPUs. It is very cache friendly. It plays to all of the strengths of the CPU, where it's just going to be constantly running through adjacent array elements on, assuming sane array data structures. But on GPUs, this works really poorly. So let's talk about why. So on a CPU, CPUs are cache-based, right? So we've got these, the way we get good performance on a CPU is we take our data and we run it in the absolute closest cache to the CPU cores. We iterate in say a stride one manner so that when we reach the end of our cache line, the CPU has had a chance to fetch in the next cache line. On top of that, a modern CPU has SSE or AVX instructions where they're going to operate on 4 contiguous data elements together. All of this works really well with this default schedule where all of them are contiguous. And I'm just going down contiguous memory addresses. But GPUs don't work like that. GPU memory controllers look for patterns. Specifically, they say, you've got 32 threads that always work together. This is something we call a warp. You've probably heard the term warp before. 32 threads. They work more or less in lockstep with each other. Now, what happens when you make a memory request? All 32 threads are going to make a memory request at the same time. And the hardware is going to look at all of those memory requests and say, all right, can I boil this down? Do I need to have 32 memory transactions, or can I boil this down to something smaller? And memory requests are done in 128 bytes. So if I have 32 threads, and I'm working in single precision, it's actually possible that if those all happen to land in the same 128 bytes in memory, that I could take 32 memory transactions and boil them down to just 1. And this is a technique known as coalescing. If I'm working in double precision, I can go down to as few as 2. If they are not, they don't boil down to the same segment, the hardware will reduce it down to as few memory transactions as it can. Well, in this first case, what's happening? Thread 0 is going to execute on 0, while thread 1 is executing on on element n over 2. That is a huge stride through memory. So the 2 threads are working on bits of memory that are widely spread out, which means the hardware doesn't have a chance to kick in. It's going to issue 32 memory transactions in order to get the memory down. But if we interleaved our iterations, so here on 2 threads, I alternate 0 and 1, 2 and 3, 4 and 5, then adjacent threads will be accessing adjacent memory addresses. Here, I'm assuming a stride 1 loop. And the hardware will be able to coalesce that. So this goes kind of back around to OpenMP was designed for a different type of hardware than what we have in GPUs. So what we want is a scheduling that interleaves the loop iterations, which you can do using the schedule clause. So what we've done here is OMP parallel for schedule. The schedule clause tells the compiler how to schedule that for. Static, so decide it right up front, but give every loop a chunk size of 1. So that last parameter is the chunk size. And you can set your chunk size to anything, but we want a chunk size of 1 that's going to interleave. Now, I need to note, a smart compiler could do this for you. These compilers haven't had a chance to really learn about GPUs yet. They're still trying to get everything implemented. So I would contend that an OpenMP compiler, because OpenMP compilers are allowed to say, actually they're required to say, our default schedule is this. That I believe that they could say our default schedule on CPUs is this, but if you're targeting a GPU, it's that. So I expect the compilers to mature a bit and begin doing this for you. And arguably, if you had the SIMD directive, they could do something similar. But currently, they don't. And so if we go through and add this to our code, so here is the 1 version. The 1 version has teams distributing on the outside, parallel 4 on the inside, with the schedule static 1. And please recall, this was the faster version before. And we do the same thing here. Schedule only applies to 4, so that's why we have it in the innermost loop. Here we take the mushed together version. And wow, I've spoken very quickly because we've made it through a lot of material. We put this together in OMP parallel 4. Collapse 2, schedule static 1. So let's think about compilers tend to work left to right again. So we'll do our teams distribute. Actually, we'll do our collapse first. Then we'll do our teams distribute. Then we'll do our parallel 4. And that 4 will be statically scheduled to chunk size of 1. So you have to read through all of these directives because OpenMP is so explicit. All right. So what is that going to do to our performance? Well, interestingly enough, both versions improved, but the collapse version improved by a lot more. And again, we didn't actually have enough time to truly follow up at a really low level what was done differently here. But this is the version that I would expect going forward to be the best performing version, because the compiler has the ability to use every loop iteration in every possible way. So you can see here, we now are rightfully so able to run this one faster than the full CPU multi-threaded version. But if I were to take that version, I didn't do this experiment. I'll answer your question in just a second. I didn't do this experiment, but if I were to take this code and strip out the target stuff and rerun parallel 4 static schedule 1, it would perform terribly on the CPU. And I think it's important for people to recognize that, because when you're writing for these different architectures, because you're dealing with an explicit programming model, you have to keep in mind that you will be writing slightly different code. And I saw a question.
Is there a reason why CPU version is just 5x improvement?
The reason it's a 5x improvement is memory bandwidth. Once we got over 8 threads, the performance started being limited by the memory bandwidth. When we got to 16 threads, it actually started going up slightly. And 20 threads, I think this was a 20-core socket, was right there level. So it all was right around 5x performance improvement. And it's all just bandwidth limited. It would have been nice to do the experiment. I probably should have, to show you where the performance would land if I had done the static schedule, chunk size 1 on the CPU. But it would actually be quite a bit worse. Yes?
Is there a way to specify different schedules for CPU and GPU in the same direction?
You know, I'm actually going to show that in just a minute. There's not a way currently in OpenMP to support different devices in the same, different devices with different schedules in the same executable, but you can use ifdefs. And we're working on hoping that in 5.0 we can come up with a way to handle that better, because ideally you want to be able to build your code for every possible device and have one executable that's able to handle that. So as a matter of fact, that leads me right to my next slide, which is, OK, knowing all of this, how am I going to write portable code? So one thing you can do is ifdefs. This is not the current version of the code, of the thing. So you can do ifdefs. You can do, sorry, my PowerPoint crashed like Friday, and apparently it saved the wrong version. You could do an ifdef that would be OMP target teams distribute parallel 4, if GPU, and then if CPU, OMP parallel 4. Or here's a little bit more creative, where I save myself some typing, OMP ifdef GPU, I'll do a teams distribute. Otherwise, I will do the 4. And then for GPU, I need to provide this collapse in the schedule. So this is, unfortunately, this is the best you can do right now, is with ifdefs. There is an if clause, and hopefully, even though this is, my presentation got broken, yes, you can do this. There is an if clause in OpenMP. It's a little bit clunky still. We're working on trying to figure out the right way to do this. But you can actually say, where is it? On the bottom here is the if clause. Again, I still needed an ifdef to handle the collapse and the schedule. I can't put an if clause on other clauses, but I can put an if clause on the target directive. So I could say, I have this variable that says run on the GPU or not. Because of the if clause, I'm going to force the compiler to build a CPU version and a GPU version. In theory, the CPU version will just take advantage of teams distribute to generate one thread team, which would be indistinguishable from parallel 4. If not, I could add more if clauses. And so if I say if use GPU, then the target will be there, and it'll offload. And if not, then it'll fall back to the host. And currently, the only way to use the teams directive on a CPU is to do a target with an if of false. Again, I think we're going to change that. I think teams is useful enough, and because clearly this is a proof of concept why people could do it anyways. So I think we'll fix that. But if the compiler didn't do a smart thing with the teams directive, you could always say if target, if teams, and it would get rid of both of those directives if use GPU evaluated to false. So it's a bit ugly right now, to be honest. And that's something that we're working on in the committee to try to make this more straightforward, especially since really at best, we're supporting 2 targets here, and really we're supporting 1 because that if-def is either on or off. And so when I build the CPU version, when if target evaluates to false, I'm still going to have the collapse and the schedule static 1, and my CPU is going to suffer. So that's unfortunately the state we have now. But as I said, OpenMP 4.5 improves the if clause a little bit. That's where I'm using the 4.5 syntax here, where you can say if target, so I'm targeting the target directive, then use GPU as my Boolean. So we did some additional experiments. First, we tried to increase the number of thread teams. So if you've done any CUDA programming at all, which I'm imagining a lot of you have, frequently you want to have lots and lots of teams to give the GPU lots of parallelism to work with. It can always, when one thread team stops, another thread team will get swapped in. By default, the way the CLANG compiler is right now, it will always generate thread blocks of size 1024, regardless of the number of the num threads that you provide, and it will be the number of SMs. Now we did try adjusting this. So you can set num teams as a clause. I didn't show the code, but you can set that, and you can see sometimes it made a difference and sometimes it didn't. Now what I would expect is on the particular GPU we're running, the K40. One thread team of 1024 threads is running each of those SMs at about 50% capacity. You can really double that, and there's still room for more threads. So we actually would have expected 2 SMs to 4 SMs, 4 times the number of SMs to work. The other thing I tried to do is I tried to say, here's the number of loop iterations, and use that to calculate how many teams. This is what you would normally do in CUDA, right? You break up your loop and just blow out as many thread teams as possible. I ended up hitting a compiler bug that didn't like that, and so ultimately I think that's probably the direction you might go. But you can see it helped in some cases, it hurt in others, but most of the time it really didn't make a difference, increasing the number of thread teams. And I think that in part is because we were really fixed on the number of threads per team. In OpenMP, you have the option to say num threads. And so most people do this at the command line on the CPU. Really, you can also do it as a clause. But the current incarnation of CLANG, and I think this will likely change, always reserves 1024 CUDA threads, even if it's not using all of them. So you might say num threads 128, and it may mask off a bunch of threads, but it's still going to reserve 1024 threads, which doesn't free up space on the SM for more thread teams to get pushed in there. And so we tried to reduce our team size, run more teams, and didn't see any performance difference because at the hardware level, at really the CUDA runtime level, we were seeing just as many CUDA threads. So this is something that I think will need to get changed. So this is generally not ideal. And really what I think will happen, this is what is generally done in CUDA, is you would adjust the num teams to say, I don't know, 128, 256, 512, something below 1024, or it might be 1024, and then use all of the rest of your parallelism to generate thread teams. This is where I expect we'll end up, but currently we're not able to do that. So we couldn't perform this experiment just because of the current state. So I'm sure that'll fix. OK. Another thing that we came across, and this is something that we've actively worked on within the OpenMP committee. So when 4.0 came out, we made a mistake. We said all variables used inside a target region will be mapped as in and out, or to and from. That includes scalars. And if you've encountered any times where you want to copy a scalar to or from the GPU, that's an expensive operation because you need to generate all of the overhead for a PCI Express copy. Now, the overhead usually goes away on large data copies, but for scalars, it's very, very high. And so multiple compiler writers, all pretty much simultaneously. I can think of at least 3 companies who made this realization almost at the same time as they were implementing this, that is really expensive. And in fact, all of them came up with this number of about 10%. That is, most of the codes they ran were 10% slower because they had to do this scalar copy overhead, which is what I'm showing here. So all of these thin slivers are basically the loop parameters. And so in OpenMP 4.5, we fixed this. And now they're made something known as first private, where everybody has their own unique copy, and they get the initial value that came out of that. And what that will do is eliminate both of these copies, because we can now make this a CUDA launch parameter. So if you've done, I know most of you have done some CUDA programming. If you've done some CUDA programming, the parameters that you pass into your function, you can pass those in that way rather than having to do a CUDA mem copy. So you can mitigate this today. You can explicitly map your scalars as 2, which will get rid of that bottom box all the way down that end. But you'll still have some additional overhead that just you can't deal with right now. So this is something we fixed in 4.5. I think the changes in CLANG are coming almost immediately. It's should be there very soon. And I think GCC may have already fixed this. I'm not sure about Cray. But so we made this change, and we expect that to get better. So let's draw some conclusions. And it looks like we'll have lots of time for questions. First off, is it possible to use OpenMP on the GPU? Absolutely. It can be done. The software is still very immature. That will always improve. There will become a point in time where you can use your package manager and it'll just install. So it's really immature right now to build. They haven't built up a lot of the GPU knowledge. One of the things that I explicitly pointed out, and I'll mention again, is around the schedule. The compiler can, and I would say probably will, learn to do that correctly. But today, it's something that you have to deal with. The OpenMP for your GPU is not going to look like the OpenMP for your CPU. As a matter of fact, we measured it. Between that first attempt, which I admittedly was kind of a naive attempt, and it's not something that we would have done, but we know people are trying to do it because we've run across codes where they're doing this, of simply relocating your existing OpenMP code. That was 148.8x performance difference. Enormous difference because it was not taking advantage of the hardware. It was written for a completely different architecture and then put over on the GPU and expect it to work. So you really are going to have to write different code for the GPU and the CPU because OpenMP is so explicit. And of course, the performance will vary significantly. So we went through, 8 iterations? Let me go back to the last graph. I feel like it was 8 or 9 iterations of the code before we finally found the best version. And I think, arguably, we could probably, once the scalar copy is fixed and the compiler gets a little bit smarter, we might get a little bit better than that. But still, what worked on this code might not work on another. So you really are going to have to try. Hopefully, I've convinced you not to try this version ever. But all of these others over here, and probably some other variations, you're going to need to try, just because the compiler is going to do what you told it to do. And so you're going to have to try a lot of these different things to find the right version. But once you do, you can see you can get good performance. So it is going to be a process for you, particularly as these things are beginning to mature. So let me go back to our conclusions here. And at that point, I'm going to thank you and open the floor up for some questions.